Okay, so for today's lecture, we will be discussing the waves part, introduction to waves, and then we will discuss the vector part. So introduction to vector, as I promised you in the last lecture, that we will review some mathematical concepts. Regarding the wave part, it's a short topic. We are going to see the traveling waves in the lossless medium and the lossy medium, okay? And we will also go through some tutorial problems. Uh, the good thing is the topic is itself is very easy, and you can spend some time to understand the formulas, and I can help you to solve some of the problems. So we try to look at the phase, frequency, the wavelength, all these parameters. This topic is important also in terms of exam because it's much easier. So, um, in my opinion, all the students should have the capacity to attempt this question in the final and the midterm. Okay. So, meanwhile, I'll show you the sample questions, how to solve it. You can also find this topic in your book. You will see in chapter 1, page number 18, right? So we have the topic of traveling waves. Uh, there are plenty of types of waves that we usually see in our daily life. Many natural phenomena, they actually produce the waves, right? Uh, for example, you see the disturbances in the water, sea waves. You see the audio production, right? The way we speak actually. So our mouth itself produces the mechanical waves, sound waves, right? So you will see that the mediums uh, around us, which is usually air, right? So the particles, they vibrate according to our sound, and then it reaches to someone else's ears, and then again produces the sensation, what we call the audio. Similarly, there are plenty of other electromagnetic waves. One of the example is X-rays, and one of the largest example is the light, right? So light itself is an electromagnetic wave. And the good thing about the light is that it does not require any medium to travel, right? And one of the proof is that the light comes from the stars, right? So you see in galaxy we have stars, right? They're in the space, and the light comes from the stars. Even though the light comes from the sun, it travels through the space, and then it reaches at the surface of the earth, right? So that means that these waves that are actually composed of electric and magnetic field does not require any medium. So they can actually be transmitted and they can travel. But there are certain other waves, such as as I mentioned, the mechanical waves, the disturbances in the medium. So if you pluck a string of a guitar, these are all mechanical waves. They require some medium to transfer. But there are some common properties of the waves. For example, they carry energy, right? So they can transport an information, they can transport energy from one point to another. We saw in our previous animation from the Hertz experiment that when the wave is propagated, if you place another antenna and if you place an LED, you would see that LED glows, right? That's how the waves, when they hit at the other terminal or the antenna, they also produce the electricity, right? Or at least they have the energy in the form of electric field. Therefore, they carry energy. But in non-electromagnetic waves, they have energy in the form of mechanical pressures, right? They could be water waves. They also carry energy, right? So you see that if the water wave is moving and the bird is sitting on it, it can travel, right? So they have the capacity to move one object from the other. They have the velocity, right? So that means they have a specific speed. For example, light travels at in 3 into 10 is per 8, right? So we also have the velocity of sound. We similarly, the other compression waves, they also have velocity. Another important property is that they are linear, right? Usually, uh, as I mentioned, the linear concept determines that if there are different sources that are actually producing some output in terms of either sound or in terms of light or another formation of waves, uh, the individual effect or the combined effect is exactly the same, right? As mean that if you combine the two sources, the effect and the if you individually transmit the effect and add them together is actually the same, right? That's exactly what you are studying in the signal processing or the signals or systems subject, right? So the evidence of this linearity is that if two people are speaking, right? So you can easily understand what language or what words these two people are saying. They are speaking at the same time, and you are listening at the same time. So there's no collision, right? Otherwise, if two people are speaking, right, their words should actually interfere with each other if they're nonlinear. And then you'll be able to, that means that they can pass through each other without collapsing each other. Although the medium or the material in which they travel or propagate actually attenuates them, make them to decrease their value with this when they pass through, right? That's what we call the medium interference. Okay, so we have based on these properties and based on the different phenomena, you can have plenty of classification of waves. But today we are only studying the traveling waves. We have transient waves that can be caused by a sudden change. For example, if you throw a stone in the water, so you see the transient, or you pluck the string of a guitar, or you have a continuous periodic waves. That means that are coming from a source that is continuously producing the waves, such as the oscillator in our case. You see this guy transmitting the light. That's a continuous source. So you have a tube light, we have a candle, right? We have the antennas, right? So they are continuous formation of waves. Uh, so these waves, you can see this is the transient wave, one dimensional. Uh, Before you see the string is straight, once you put a jerk on it, you see there's a disturbance in the string. Actually, this disturbance is called the wave. And you'd see that this disturbance actually travels along the direction of the string, right? So it's generated here and then it starts traveling. So this u means that it has some velocity. So it's traveling with some velocity, right? It could be two-dimensional, right? Depending upon the medium, right? So if you have a pond of water and then you make a sudden disturbance in the pond, so it will generate waves, right? If you carefully look at the wave patterns, you will see these are the sinusoidal waveforms. There are plane wave fronts in the form of planes. So the wave actually travel to the direction. There could be cylindrical wave fronts, right? So the wave formation is in the form of, there could be spherical wave front. So the wave formation is in the form of a cylindrical. So there could be different sources. Just like your tube light, you see it's round, right? So it's like a cylinder, pure cylinder, right? And if you look at the flame of a candle, right, it's like a spherical, like this round shape, right? So the waves, the shape actually depends upon the source, right? Before we move further, let's look at this property uh, of the wave. So this will help you to understand the concept of traveling. Okay. Now, I must say that this concept you must have seen in the convolution. Have you studied it in your other class, the signal system or linear systems, right? So you will definitely see this. Remember, for every function, right? If you see this t minus something, right, that has a special meaning. Uh, you can have three possible types of arrangements with your function. One arrangement is that you multiply something with your function, right? Let's say you multiply it with 2, 4, 5, 6. It means that you are actually increasing the amplitude, right? So you are making your signal bigger or your wave bigger. That means the intensity, amplitude, or voltage of that wave is now getting higher. In fall is the volume, right? So if this A is bigger, your volume is bigger. That's amplifies something. Understand? Now, if you multiply something with the T, right? Just T, what does it mean? If you have A f of T and you multiply something with the T, let's say 2T or T by 2, what does it mean? What this will happen? That's the play speed. Your signal either got compressed or expands. So it's multiplied 2T. That means that you are covering the distance twice. That play speed is twice. If it's T by 2, that means it's slow mo. It now takes 2 times to cover the distance, right? But the third operation is if you add something or subtract something in the T. Now, this is very important. This means that if your signal is here, if you subtract something, you are displacing it on the axis, right? So you're moving it something. That's what we call traveling, right? So if your phone covers some distance, that is actually subtraction. Understand? So now, because this is time, right? And you are now moving this waveform to another point and another point. So you move x over u, right? X is the distance and u is the velocity, right? So actually velocity is meter per second or distance per second, right? And distance per second, and then you have x, actually it's time, right? Actually you are moving t minus 1 second, t minus 2 second, t minus 3 seconds. That means you are not displacing it on the axis. It's called the shift, right? It's called shift. So either you can drag it on the right side or either you can drag it on the left side. That's the direction of travel. So now this shifting will help you to move your signal. Okay. Now let me repeat again. So you will see three different kinds of arrangements or operations with your signal. One is you multiply something. If you multiply, then your signal get either bigger or smaller. That's called the amplification. Another is you multiply with T. That means that you make the things able to shrink or expand, right? So signal becomes shrinked or amplified. That's 2 times, 3 times. It's similar to the play speed. Third thing is the addition and subtraction with the time. That means you are actually escalating or you are actually shifting your signal left or right, right? Now this can happen to signals, this can happen to waves, right? Any mathematical function. The answer is only like this, right? So we can see that this part now is at T not U, this one is T1U, and this one is T2U, right? That's how you move the signal. So why we are looking at this? Because we want a formula for a traveling wave. We want to see how a wave travels. Understand? So that means that if we subtract something from the time function, then we can make this wave travel. Okay, so we use this concept to understand. Now let me show you how the traveling wave. So you see, this is your traveling wave. You see. Now what is this? This is the peak value, right? So the peak value is your amplitude. Understand? And there are two peaks, and the distance between two peaks is the wavelength. Or one of the wavelength, one over wavelength is your frequency, right? That means number of cycles per second is your frequency. Now, the third thing is, you see this peak is traveling, is moving, right? And it has to be with some rate, some velocity. Either it's moving too fast or too slow, right? And that thing is determined through this function, x over u, right? If your u is bigger, you're moving too fast. If u is smaller, that means you're moving slower, right? So you see, this subtraction and addition helps you to drag your signal on the left and on the right. Now, again, this concept is again used in polyphase circuits, three-phase circuits. You would see that usually how to write a formula of a simple power circuit. Let me show you. See, you will see the power function of simple, let's say, right? You will see the simple voltage function in this form. That's a simple sinusoidal waveform you can see in the AC waveform, right? Or you can have another waveform, right? So you see, again, we have a minus sign here, right? Right? That means that if you have one waveform like this, and then you can have another waveform like this. You see, both are dragged on the x-axis, right? So this minus sign here or plus sign here will actually move that your signal either move left or right, right? So we use this concept to understand the traveling waves, right? So how the wave actually moves on the on the distance or on the planet or on the earth, right? So you see, that's the traveling wave. Now this is the, you see, standing waves. You see, that's a standing wave. Similar, you pluck the string of the guitar and it moves up and down, right? See, they do not carry energy, right? They cannot transport the energy. You see, that's the traveling. Now this is your traveling wave. You see, your wave is actually traveling. Okay. Now we will use the topic sinusoidal waves in lossless media. Now this equation is actually important, right? Later I will solve a problem on it and show you that what type of question can be asked in the exam. Now, uh, let's assume we have a wave. Now, all the waves, traveling waves, we are now looking at their amplitude, we are looking at their frequency, we are looking at their speed or the velocity, how fast they are moving. Understand? So now I can have two variable. One is x, right? That actually means distance, because it's a traveling wave. So our wave is traveling and covering some distance, just like a car. Another unit is time, right? So how long it takes, right? So another is a time axis, because the wave itself is also have some cycles per second. Okay, so if you consider them individually, then you can understand it. For example, look at this thing. Let's assume that you have an oscillator and your oscillator has produced certain cycles, right? Maybe piece of a wave, right? So this piece has two cycles, right? Now currently two cycles. And we have time axis to show this, right? 0 to t. This has a complete cycle, you see? That's a complete cycle. The time when it starts, the time it finishes. And then you have another cycle. Let's say it's two cycles, right? So one peak to, that's capital T, that's the time period. the time it takes for a complete revolution, right? Understand? Now, I want to compare this with our physical example. For example, have you seen the running escalators, right? On the MTRs, we have running escalators, runners, right? Maybe in the central you have seen, right? So, have you seen that people usually walk on them, right? And the escalator is also moving, right? So that's the example of a kind of a traveling wave. Those people who are walking, it's a pattern, right? So they are like this waveform, right? And the escalator is moving. That means they are walking and moving, walking and moving. So this is the steps, right? And then this X is the escalator. So a wave is vibrating and also escalating. Understand? So the vibration is cycles per second and the motion is escalation, right? So if you want to see, just imagine this thing, right? You see? So it's vibrating and it's traveling. There are two functions. One, it's its frequency. You see, it has a frequency, right? So number of cycles per second. And it also moving on the x-axis. It's not just staying itself. Is it clear? Right? So it's vibrating plus it's running. Right? You see, it's running on the right side, not standing. So that's the running part, and that's the vibrating part. So in vibrating part, we put the running 0 so we can see the cycle piece of the wave. And then we put X so we can say that wave is moving. Remember, this lambda is actually spatial wavelength. Spatial stands for the land, right? That the wavelength that it covers through the land, right? So you see that it actually covers lambda. That's the distance on the x-axis. Now at t equals to 0 and x equals to 0, that means this is the piece of wave and now it start moving, right? This phenomena can be explained through this equation, right? So we have A cos. So A is the amplitude of the waveform. That's the amplitude of the wave. That means that the internal or the maximum electric field strength, right? So if you increase the A, that means you are increasing the voltage of the waveform. 2 volt, 3 volt, 5 volt, right? That's the transmitter's power. How much power, how much voltage it has to be transmitted, right? Now, this 2 pi t over t, this capital T is actually frequency, right? Because 1 over t is the frequency, right? So that means how much kilohertz, megahertz of the oscillator you have. So if this t is small, that means your frequency is high, then this thing will compress like this. Minus, remember in the last slide, I told you that this minus or the plus stands for motion, right? So this is oscillating part and this is escalation part, traveling part, movement part, shifting part. So in mathematics, we call this shift, right? Now, this shift is also changing. The variable is x, right? Because of course it's covering some distance x, right? So it's running in meters. So this x is in meters, right? And this phi is actually the initial phase, right? Sometimes it's 0 or sometimes it's 90 degree or whatever. So we have this complete equation. Now we need to derive some important concepts from this equation. And before we do that, let's look at this equation again and we see. You see this is moving, right? So this point is actually moving. You see, this point is moving, right? The same concept we have here. We will consider an arbitrary point P and we will try to examine slide by slide. So we see that what happens when some time passes. Now you see, at 0 time, the wave is here. That means this is the starting point. right? And after some time t by 4, right? So this part of the wave, so this is the part of the wave that actually we are examining. We are looking at this part. After some time, this part has now moved here, right? So that means it has escalated on the right side. That's because a traveling wave, so it has traveled here. Now, how faster it has moved, it depends upon the phase velocity, right? So keep on changing the phase and it will start running, running, and running, right? Now, after again t by 2 time, this part has moved further. You see, the point P is traveling. Previously, you are here, and now here. Now you see it's moving on the right side. That's how you can examine the wave actually is moving. Because in the slides, we do not have animation, right? So this is the way to explain this concept. You see, it's actually traveling, traveling. Now, uh, we are interested in finding the frequency. So what should be the frequency? We are interested in finding the lambda, what should be the wavelength. We are interested in finding the velocity, how fast it's moving. Okay, so these three things are important. Now I help you to derive this, right? At the end we will use the final formulas to solve it, right? So let's see how we can derive. It's a very beautiful method to solve it. Okay, now let's consider the same equation that we derived before. Forget about the initial phase. Okay, just forget about this thing. Okay, consider the same equation and call it anything y naught. Let's say after 2 seconds and covering 3 meters, the amplitude is, let's say, y naught, right? Because it has some amplitude, right? Y naught is some value of the electromagnetic field, let's say 10, 12, 13, 14. Okay, now uh, we can actually remove this part to other one, right? For example, if you have y naught is equal to a cos theta, actually we can separate the theta. So theta is equal to y naught over a, and then we can use cos inverse, right? So we can use mathematically this thing. I can solve it here. If it is a cos theta, then y naught over a is equal to cos theta, and theta is equal to cos inverse y naught over a, right? That's how we use mathematics to separate out any angle, right? You know, cos theta is pi by 2, then theta is equal to cos inverse pi by 2, right? So how to separate out this part? So we use a come here, and then cos inverse come here, right? So now we have separated out this internal part. One important thing about this thing is that all these values, the answer must be some constant value. 1, 2, 3, 4, 5, 6, that's it, right? So we call it constant. That means it has some value, either 2, 3, 4, or whatever the value. Whatever should be the answer, it should be constant. Remember what we are interested? We are interested in the velocity, right? So let's take the derivative on this side. And I would ask you why we should take derivative here. Why we should apply mathematical derivative on this side. So anybody knows what's the formula of velocity? Yes. So speedometer, right? What's the velocity? Dx over dt, right? Remember? Some people like this. Change in distance over change over time, right? So let's say you take 2 meter to 6 meter, and the time goes from 3 second to 8 second, right? Remember, let's say you start from 4, right? And you move to 6, and then the time starts from 2 and move to 8 seconds. So what's this velocity? 6 minus 4 divided 8 minus 2, right? Distance covered divided by time. In mathematics, we call this dx over dt, rate of change of distance, right? Your speedometer is every time doing this, change in velocity per time, right? Is this clear? Is this clear? Velocity is distance over time. That's why we need to take the derivative so we can find out the velocity. Now take the derivative on this side and this side, both sides, because constant derivative is 0. Constant derivative is always 0. Let's say you take the derivative of 2, it's 0. Take the derivative of 10, it's 0, right? So the answer is 0. Take the derivative of here, t over t, because t derivative dt over dt is 1. Therefore, you see 1 here. Now we have dx over dt. That's the reason why we took the derivative, because this is our velocity. Actually, we are interested in velocity. So we find out that dx over dt here after simplification is lambda over t. That means that for this waveform, if you know the spatial wavelength, if you know the frequency or time, you can find out the velocity. Correct? Right? Or 1 over t is lambda, so f lambda is the velocity. That means you change the frequency, it moves faster. You change the spatial wavelength, it moves faster. Right? That's how you find out the parameters. Okay. Now, this whole derivation is for your understanding, right? The only thing that you should be concerned regarding the exam is these formulas. Okay. You should know that when a wave is given, how to find out the frequency, what is frequency, how to find out the velocity, and what is the velocity. Okay. So now we have a final equation in the form of this one. Some people prefer to make it into simplified form, right? So what we can do is we can call this guy omega and we can call this guy beta to make it simpler, okay? So that we can memorize it, right? And then we can say that, okay, omega is 2 pi f and beta is 2 pi over lambda, right? So once you know these two things, then you can find out these two things. It's clear? Any problem in the derivation? You can ask. Do not hesitate to ask. Just raise your hand and I can explain again. Okay, let's move further. Another important thing in this equation is the sign here, this signature here. If this is minus, remember if your signal or your wave has a subtraction sign here, that means that it's moving on the right side, right? In your next subject, you will study these kind of functions, okay? That's a simple square waveform or a step function, right? This is xt and the same point here. You will study this one. You see? So you see, if we subtract something, it moves on the plus x direction, right? Same in signals, you study this one, and in power engineering, you study this one. This is your voltage waveform. And when you add something, your voltage waveform becomes this thing. If you add something, it moves on the other side. If you subtract something, it moves on this side. Right? Same concept. If it is in wave, wave is traveling. If it is in signal system, the step function is moving. If it is in polyphase circuits, you have another phase. Okay. Remember, in polyphase or three-phase system, we do not talk about the time shift. We talk about phase shift. Actually, it's same thing, right? In concept, it's same thing. So we have three different waveforms in one cycle, but they are separated by 120 degree, because 120, 120, and then again 360, right? So we have three waveforms in one cycle. Okay. Now, if there's a positive sign, that means that waves travel in the negative direction. That means that if your movement is like this, and then you have another thing, so that means that x of t plus t naught. In power engineering, we use another term. This one we called leading, and this thing we called lagging, right? So when you will see the power factor based corrections, you will see that the effect of adding the capacitor to the network or to the system will help you to improve the power factor, right? So the same concept. Lagging means it's lagging behind, coming after it. Leading means it's leading or arriving earlier, right? So that's the positive case. Mathematically, they have the same structure, same formula, same representation. So the positive thing in the time means you escalate the signal on the left, negative axis. And negative means you escalate the signal toward the positive axis. Okay. So this will help you to understand the lead and lag concept in capacitors and inductors. This will help you to understand the linear time invariant system. This will help you to understand the polyphase circuits. Okay. So it's a quite a common concept when you subtract something in your signal. Okay. It's clear? Okay. Let's look at the lead and lag concept again. So these are the three waveforms. Okay. Remember, in actual three-phase circuits, we have, let's say, if this is 0 and this is 2 pi, right? Then this is 180 degree, right? So 120 should be somewhere here. Okay. So in polyphase circuits or three-phase power circuits, remember you should have a 120 degree fixed phase shift, right? But these looks like three phase, but actually they are very close to each other. They are not the three phase, but there is a difference in phases, right? So now you see, uh, the blue one is actually a pure cosine wave, because its peak is starting from the 0. It's a pure cosine wave. If I have to write a function, I would write a y a is the amplitude, cos omega t, right? Why omega t? Because there is 0 in addition, because it's starting from the 0. There's no shift. So you can directly write a cos omega t, right? Now, other waves must have some reference with respect to it. Now, the green is lagging. We use the term lag. That means that it's coming after it. It's delayed. It's late, right? So you see, the amplitude of the green one is delayed. How much is delayed? You have to look at here. right? So it's minus pi by 4, right? If I want to compare the green one, then I would write the green one, same amplitude, same cosine omega t minus pi by 4. Why minus? Because it's on the right side. It's delayed. It's lagging, right? You will also see this concept in the voltage and current in capacitors, right? In AC circuits, when you study the AC circuit, you will find a similar concept. The voltage and current within a capacitor actually lags behind each other, right? Now look at the red one. So red one is arriving earlier than the reference. So we can write A cos omega t plus pi by 4. That means that it's pi by 4 ahead of the reference. Is it clear? Now you see the concept is exactly the same. So this is our traveling wave equation. Remember, this will tell us the direction of travel, where it's moving, right or left. Okay. Can you spend some time to solve this problem? I remember we asked this question in maybe some late assessment exam. Okay, we asked this question. So you have three waveforms. The waveform in red is given by cos 2 pi t by 8. 5 cos 2 by t by 8. 2 pi t by 8 is the reference waveform, red. So what should be the value of green wave and what should be the value of the blue wave, right? Okay, so one thing we need to understand is what is the total time period of wave. Now you see the let's look at the blue wave because it's more ideal. It's starting from 0, but actually you can use any of them to see. Can you compare two peaks of any waveform and see the x-axis? For example, the blue starts from 0 and blue ends at 8. So the distance or the time it takes to complete one cycle is 8 seconds. Is it correct? Makes sense, right? And it's true for all the other waveforms. For example, the red one starts from 0 and finishes at 8. You see, this peak to this peak is 8. Blue, the peak is 2 and the peak is 10. Again, 8. You compare any two, repeating points and you will find the x-axis is 8 seconds, right? So that means that it completes one cycle in 8 seconds, right? Okay. So how many radians are there in one cycle? In one cycle, we have 2 pi radians. The complete cycle is 2 pi, right? So cosine starts from 0 and then pi by 2 and then pi is 180 and then it goes to 2 pi and then goes again, okay? So for example, those who do not understand will like this: 0 pi 2 pi and then again 0 pi 2 pi 0 pi. That's what we call a complete cycle, right? This is 180 degree, and this is 360 degree, and this is pi by 2, right? So you can have any pi by 1, 2, pi by 3, pi by 4, pi by 5, and then you can move up to 2 pi. This is what we call the cycle, okay? So one cycle is 2 pi. And so what about this 1 unit, small 1 unit? You see, we have actually 8 units. 1, 2, 3, 4, 5, 6, 7, and 8, right? Right? And then if it is 2 pi, that means that one of the point is, yes, so one of the point is pi by 4. Why we did this? Because we will find out how many units each waveform is moved, so we can easily find out their distance. For example, red one is at the central location, ideal location, so its displacement is 0. Now look at the blue one. How many units blue is far away? 2. 2 units away from the red, right? Its peak is 2 units on the right side of the red one, correct? Right? So 1 unit is pi by 4. 2 unit is 2 pi by 4, right? So one unit is pi by 4, right? So red one is 2 units. So this red one, red movement is 2 units, right? That means 1, 2. Sorry, the blue unit. Blue is 2 units on the right, correct? That means 2 times pi by 2, because it's on the right side. So you see, the 1 unit is pi by 4. It is minus pi by 2. So its phase is minus pi by 2. Yes. Sorry. Yes, please. It's okay now. Okay, so we will find out now the voltage should be amplitude is 5 cos 2 pi over 8t. That's the same frequency, and its movement is pi by 2, right? And this is actually equals to 5 sine 2 pi by t by 8, right? Okay. Actually, we can use the same formula. So this is equal to 4. Actually, there's a small trick in this question. The cost representation, right? Where? Now, look at the green one. So, how much green is deviated from the blue one? So, if you look at this green one, actually, green one is here, right? So, you see the difference between green and red is only 1 unit. So, green one is 1 unit earlier than the red one, right? So, we can use the same equation with the blue one, 5 cos 2 pi t over 8, because it's advanced version, right? Plus pi by 4. So this is for the green one. Okay. So for the green one, because on the left side, it's leading. Therefore, we will add pi by 4. Okay, this is for your understanding of, okay. The second option. Second option. Yes, green. Second option is green one. Okay. Okay. Uh, so previously exam, we asked the same question. Okay. All don't look at the solution. Uh, we studied the wave equation right before, right? So A cos omega t, right? That's beta t, plus or minus x something, right? Look at the equation. What's the equation of the wave? Right? Look at the equation. So you have A cos omega t minus beta x. That's the equation we learned, right? Right? Can you compare? And while comparing with the main equation, find out the values. Let me write it and then you follow the steps. Please don't look at the solution. For example, so our equation is A cos omega t minus beta times x, right? And We also have, let's say, plus phi naught. This is the equation. How to compare? So omega is what? 2 pi m, right? We derived earlier. What is omega? Omega is this thing, because this is t, right? If omega is equal to pi into 10 to the power 7, omega is 2 pi f. You can find out frequency, right? Can you solve it? And then look at this. Because this is not x, this is z. Just to think that actually could be x, y, z, and so x counterpart is z here, right? So what is beta? Beta is pi over 15, right? Then find out the lambda. Look at the formula and find out the lambda. Pi naught is 5/6. We don't need it now. Right? Compare and find out frequency, lambda, and ut. That's it. Just compare it and find out the solution. So where to find out the formulas? Use these formulas. This is your omega, right? Omega is 2 pi f. Anything with the variable x or z is beta, that is 2 pi or lambda. Use these equations to for comparison. T and this part is omega. Z, x, and pi over 15 is your beta. Put beta here and you'll get lambda. Put omega here and you'll get f. F and lambda is your velocity. Okay. 10 marks. You know what is the trick? So the trick is that people try to find x in the equation, because this equation is for xt, but this equation is for zt. Actually, same thing. X, y, and z are three directions. It could be x, it could be y, it could be. Understand? People believe that x is the only direction you look at. But three directions. X, y, z. And x, beta x, beta x, x, beta x, right? You see, so it's x. This is not the next. Okay, now look at the solution. That we studied before. So compare this equation with the question. Okay. So if you compare this one, you see that A is 10, right? And in place of 2 pi f, we have this one. Okay. So here we have x variable, here we have z variable. So x is in part of z. Therefore, 2 pi over lambda is equivalent to pi over 15. Okay. So again, this is omega. So omega is pi into 10 raised power 7. And omega is also equal to 2 pi f. 2 pi f. And f is omega over 2 pi. And place the value of omega and you will get 5 into 10 raised power 6, which is 5 megahertz. That's it. Now, 2 pi over lambda is pi by 15. What's the value of lambda? So pi cancels pi. So lambda is 30 meter. We know the lambda, we know the f. Then up is f lambda. F multiplied by lambda is the spatial, the speed. That's it. Just comparison, one-to-one comparison. Then how to find out the direction? Look at this sign. The sign is positive. That means it's moving on the left side, right? It's leading side, moving on the plus axis, minus z axis. So the question can be asked like this: determine the direction of wave. That means if there's a plus, put the negative. What is the frequency? Because omega is 2 pi f, f is equal to omega 2 pi, frequency is 5 megahertz. What is the wavelength? Right? 2 pi or lambda is wavelength. What is the velocity? Up is the velocity f lambda. Once you find one thing, then second, then third, finish. Is this clear? It's difficult or easy? How many of you believe it's difficult? Not difficult at all, right? Yeah. Need your opinion. Okay, yeah, that's fine. Good, good. Okay. Let's move to another part. Okay. If you want a break, we can take 4 minutes or 3 minutes, 5 minutes break. Okay. Yeah. Please come quickly. Okay. We start very important lesson again. Okay. Yes.
At this page.
Yes, yes, sure. Attendance, I already gave. After you finish this class, you have right after you finish the last one. So you have time for the next one day. Please spend at least 1 hour to look at what we have done. That's very good for you. Because in one class, because you have 3 hours lesson, it's very difficult to digest all the things in one lecture. Once we revise it, it will be very good. Okay, let's continue. Okay, now in actual, when we consider the motion of the waves, uh, we see that the wave actually attenuate themselves when they travel. Okay, so this is we call traveling in lossy media, right? So what happens that the medium, it actually deteriorates or attenuates the amplitude of the wave. Now, how to write this or represent this using the function, we add one extra thing, a e raised power minus alpha x, right? So we call it the envelope function or exponentially decaying function, right? So you would see this kind of function in different real world problems, right? So you see the nuclear functions or nuclear reactors decaying at exponential rate, right? You would see some stock exchange processes following this function. Even the capacitors, the charging or discharging functions, they follow the similar trend. And we use e raised power minus alpha x to represent these functions. Okay. So when you multiply this function, when you multiply this function with the waveform, you would see that it actually attenuates the wave like this. Okay. We call it the lossy medium. So this alpha actually, this represents the medium, the property of the medium. We call it attenuation constant, right? That actually represents how severe is the medium in terms of damaging the wave. Okay, please. So rest of the solution is exactly the same. Now we will add this e raised power minus alpha x to the functions to see how it can attenuate, right? This wave, I would suggest you to use it as a homework. Okay, the solution you should follow it. Okay, understand? So I have the solution, you solve it. And this question we also asked in the previous exam. Yes, yes.
Who or green? I missed this.
Okay, no problem. You can write this one. This one is
This one is
blue, red, and green.
then maybe
No, no, I can write it for you. Okay, so this one is, first one is blue, right? Red, green.
maybe sure, but I remember this line is the red. Maybe on
Oh, sorry, this one.
this one.
Oh, sorry, this one is different. This one.
Not this one.
Oh, this one is. This one is. The first one is.
I just missed this.
Okay, the first one is green. The second one is blue.
Okay, this is the full and
Blue one. Blue one.
this one is A and sine
Omega t.
plus S zero.
Plus 0. Yeah, 0 means nothing.
Okay.
Okay, thank you. Okay, so look at this problem here. So we have, attention please. Please listen. Please listen very carefully. We have an electromagnetic wave which is propagating in the z direction in a lossy medium. Okay. So when we talk about the lossy medium, then we know that we can use this function. y a e raised power minus alpha x. Okay, so we have the output of the waveform, which is initial input or amplitude. E raised by minus alpha is the attenuation factor, and x is the distance, how much it has traveled. Now, if alpha is given, if the wave's electric field is 100 volt per meter at z equals to 0, right? That means that we have something like this, okay? And that's our envelope. That means the wave is attenuating. So, uh, initial amplitude is 100. So, anybody can tell me what is this value? What does this 100 stands for? Amplitude. That's electric field, okay? The amplitude or the electric field of the waveform is 100 volt per meter. That's the initial amplitude. At z equals to 0, that means this axis is z. At 0, it's 100. How far can the move? So how far mean find the distance. Can the wave travel before its amplitude is reduced to 10 and 1 micro? So let's say if the amplitude is here and it's now 10 volt per meter. So the question is, if you know the medium, zero point 0.5, and the initial amplitude when we transmit the wave is 100, and then how long it takes the wave to reach at 10 in terms of a distance. So what should be this distance? That's the question. So we use this formula, y equals to a e raised power minus alpha x or alpha z. Okay, so amplitude is 100 given, alpha is given 0.5, and z we have to find, and the remaining amplitude is 10. Okay. Okay. I have seen many students make mistakes. They do not know where is 10, where is 100. So sometimes they put 100 here and 10 here. Make sure that this 100 value means that the value at the starting position. Amplitude when the wave was originated. That's a peak amplitude. Remember, this is your peak value. And this is output value. That means after traveling some distance, what's the output? Okay, so that's 10. So that's how you can differentiate between 100 and 10. 10 is the output, 100 is the input. Okay, now the question is how to solve this. So you divide this 100 on the right hand side and you'll get this thing. Now remember, for exponential functions, we always use natural log on both sides to solve the problem, right? So natural log will cancel the exponent, and then you will get 0.5z equals to natural log of 0.1, and you will get minus 2.3, and then z is equal to 4.6 meter. That means that if the alpha is 0.5, then z is 4.6. Is it clear? Then I will tell you another trick in the question that can be asked in the exam. Everybody's clear about this question? Then I proceed. Right? It's clear. Okay. So in one exam, That means medium itself is more attenuated. The previous case, it was reaching at 10 in 4.6 meters. If the medium is strong, it takes 2 meters to attenuate it. That means alpha is something that defines the quality of medium. Let's say if your cable is broken or your medium is too noisy, then it will not allow wave to move further. Definitely, it will attenuate it a way ahead of time. Right? If the medium is friendly, alpha is small, it will not attenuate too much. Then the wave with the same amplitude can travel far. Maybe after 10 meters, it can still have the 10 volt per meter value. Understood? So I asked, compare the two values of alpha with your answer. Again, the same question, the same solution you have to think about. Okay? Okay. Now, B part, let's see. Now the voltage we ask is 1 volt per meter. Let's say this is 1 volt per meter. What should be the distance? Put the value with the same alpha, and you see it takes 9.2 meters to attenuate it further. Now, 1 microvolt. Remember, 1 microvolt is 10 raised to power minus 6, not 1. Okay. Then you see maybe 1 microvolt is here. Now it takes 37 meters. Is this clear? Yes, please let me do one. It's actually this is not television, and the rest of the part is cosine. Right? That's okay. Now, just listen. Now it's our fun time. Okay. Now it's our fun time. We have enough mathematics, and let's talk about some different applications in electric fields and magnetic field, right? So at the end of the chapter, you would see plenty of applications, right? I usually call them student read. So I strongly recommend all of you to at least read one time. These are very important because in exam, I will ask one case study from our daily routine applications. Okay, so if you read this, you will have very good concept. Okay, so anybody knows what's the difference between photoelectric and photovoltaic? So in 1839, there was a young scientist, Edmund Becquerel, 19 years old, right? He actually discovered that if you have a piece of platinum electrode, let's say simple platinum, a simple piece of electrode, and you hit some photons on it, right? It will emit an electron, or it can actually produce some current. That's called the photoelectric effect. That's how an electron can be emitted from a material when some photon or some light with some energy hits on it, right? And later on, uh, the famous scientist, uh, the Albert Einstein, he actually figured out that E equals to hc over lambda. That a if the energy gap of the material, that the electron is binded by the material, if a photon higher than that energy gap hits the surface, right, then it can actually remove one electron, or it can actually pass that electron from the material, or evacuate an electron. And this is the reason why Einstein was awarded the Nobel Prize. Okay, explaining this photoelectric effect. Okay, so h is Planck's constant, c is the speed of light, and lambda is the wavelength that the light strikes on it. So E is the energy gap. So because this single material is not enough to provide the current, this one is only responsible for emitting an electron. Now, how to convert into electron into the current is to receive that electron, collect that electron, right? Now, if you make some doping of these materials, one with the N type and one with the P type, right? That means that the electrons and P type with the holes. You all have studied the PN junctions, right? The semiconductors. That means the doping. If you perform the doping and make one material N type, right, and another material P type, and connect them, then when a photon hits, it can extract one electron based on this gap. And then the P type, because the amount of electrons are in less manner, in negative manner, right? So these electrons can fill the holes, right? Because the deficiency of an electron is known as the hole, right? The amount of no presence of electrons. And here the electrons are in abundance, right? Because we do the doping. And then based on those bonds, we have excess amount of electrons. And this n time, when the photon hits on it, it can, you know, create an electron because there's an electric field of those materials, right? There's an electric field of p-type and n-type materials, right? So that electric field now can capture the electrons and move to the p-type, right? So if you have some load here, right, it can actually pass the current through the load. That's how you can actually produce a DC current or DC value. This principle is known as photovoltaic effect. That means that it actually can have a voltage or potential difference between the two materials or two plates, right? So this is known as photovoltaic effect, and this is known as photoelectric effect. This effect is responsible for generating photovoltaic. They are not same. Okay. Now, where we use this effect? Yes, solar cells are made on this principle, right? So here we have a glass cover, we have anti-reflective coatings. So when the photon hits, they can be captured inside, because the efficiency of this cell depends on how much the photons hit on the surface, and how much energy they can you know uh, evacuate based on their incidence. And there's a front electrode, there's a p type, and then there's a back conducting layer, and then we have a load layer. So you see the light photons, they hit on the surface, and then because of the coating, they start hitting on the all the possible surfaces, and then you can collect the current, right? But there's a problem here, because the light that hits on the surface, the spectrum is quite wide, right? It has a range of frequencies, right? Because we are talking about the spectrum of light. It has a range of frequency, not a single wavelength, right? That means that only a small spectrum of light can actually extract the electrons. The rest of the spectrum is useless, because this amount of electrons that is given out, right? It depends, the energy depends upon that wavelength, right? So but our wavelength is quite wide. So what we can do is we can improve the performance by using different types of materials, such that each material is responsible for each wavelength. For example, 200 to, let's say, 500 wavelength, our first material semiconductor is good. And the other wavelength, we have another material, another wavelength, we and another material. So we make use of the all possible energies of different material and try to improve the efficiency. So this method improves the efficiency 3 to 4 times. And this makes a single cell, let's say 6 volt, 8 volt, or 12 volt. And then connecting these modules into the combination of series and parallel, we can have a PV module. So cells make module, and module make array, right? So you can control or adjust the amount of voltages. Let's say if you connect all the cell in parallel, then you can actually build up a strong current, right? So the amount of current that it produces is very high. So if you put them into a series parallel and make the voltage, let's say 24 volt, then you can reduce the current, but the power still remains the same. That's how our conventional, the solar system works. Remember, they generate pure DC, okay? And we have simple IGBT based DC to AC converters, right? The circuits that we use in the UPS, uninterruptible power supplies, or we call it DC to AC inverters, right? So this DC, by using the electronic switching circuits, we convert this DC into the AC, and then of course we can use transformer to step up or step down. The part of a DC AC that we use can be directly used to light up our household, and we can also supply this to the grid, right? That's what we call the green metering. Let's say your daily consumption or the load at home is, let's say, 5 kilowatt, and in the daytime when the sun is at the peak, and you are actually generating, let's say, 8 kilowatt, so 3 kilowatt you can pass to the grid, and it can be added to the grid, right? And then in the nighttime, you can use the same units from your power supply company, right? So they can charge you with some less amount or maybe even higher amount, and then you can again use those energy. Another possible way is you use this DC to store into your DC system, battery systems, okay? And then when you require them, you can actually you run a load your at your own storage, right? Because the generated DC is usually higher than your daily consumption, okay? Okay, that's the end of the first part of our introduction. And now we look back to the vectors. Okay, so this is our mathematics part. Remember in the wave portion, uh, you will be asked at least one question either in midterm or in exam. Okay. So if you prepare the waves properly, you can easily handle one question. Okay. At least 10 marks. Okay. In this chapter, we will look at the basic laws of vectors. What are the coordinate systems? Uh, we will not look at the transformations. Although we can transform or move from one vector to another vector system, we will look at the application global system. We look at the gradient. We look at the divergence, right? This is not in the exam. Okay. Vectors, these are all for your preparation. Okay. This one, gradient, divergence, and curl, these are also important in terms of exams. We usually ask at least 10 marks here, 10 marks here, and 10 marks in waves. Okay. So after completing this chapter, you would have one exam question. Yes. Sorry. No, just two parts. One part is for the from the waves, and one part, let's say, find out the gradient of a field or divergence of a field or curl of a field. Simple solution. If 20 marks, then five questions. If 25 marks, then four questions. Yeah. Not yet. Because if the question is difficult, then 25 marks. If it's easy, then 20 marks. But we will make it clear before the exam. Yeah. Okay. Let's look at the vectors. Uh, so, so how many of you have previously it or learned about the vectors? Good, good, very good. Anyone else? Oh, sorry. Forget. I say. Anyone else? Any definition of vectors? What are vectors? Yes. So those physical quantities that has magnitude and direction are called vectors, right? So when we solve them, uh, we cannot directly add them to other quantities because they have their special direction. Okay. Uh, Let me give you an example before we start. So let's say uh, okay, let's see. There are two people. They are pulling a cart. Okay. Yes, a cart. They're trying to drag one box. Okay. One is dragging like this, another is dragging like this, right? And they are applying the same force. Which one is better? Same surface. Maybe person two is weak then. Let's assume same person, maybe twin brothers, born at the same time, same height, same width, same power, same box, same string. Everything is same. Also not thirsty, powerful. Yeah, just drag. No, no, no lift, no lift, just dragging. Same friction, everything is same. Also brothers. No, same friction. No, no, I'm saying that same force, same friction, everything is same. Which one will move, I mean, more far away? Person two. Because the direction of the force makes it difficult for person one. Now I tell you why. One thing you can already see that because the the motion is, or the displacement is along x direction, right? And the force here is also along x direction. Now this force, the first one, making some angle theta, right? Yes. So F cos theta is moving here. In this case, the work done is actually F cos theta, force times distance. In this case is F times x. This cos theta is always less than 1 because of this angle, right? So that means that if I say this F is 5 Newton and this F is also 5 Newton, so force is same, everything is same. Result is different because the component of that force that along the direction of distance is less than this force. So that means that vector quantities need to be solved before we can calculate, right? So that's the power of vectors that can help us to analyze the quantities. Okay, that's why we use vectors. Now, this is true for other concepts. Let's say this is true for the torque. Torque is vector quantity. This is true for the work done. This is true for the force and many other, just like electric field. When we calculate the electric field, it has similar vectors and similar directions. Now, so vector is clear, right? So let's say I have two phases, right? Right. One is at 0 degree, another is pi by 2 degree, just like polyphase circuits, right? Or if I three phase, are they vectors or not? Because vector quantities, they do have the direction theta. I have the direction theta. I have the amplitude 5 volt 90 degree, 5 volt 0 degree. So if you remember when you solve those questions, sometimes you like this V angle 0 degree. Are they vectors? Yes or no? No, we cannot add them, right? Okay. Remember, in electrical engineering, uh, we use this type of mathematics to solve the voltages in transformers, in motors, in AC circuits. But these are not vectors. We have a special name for them. We call them phasors. Phasors. If you look at the electrical engineering book, there should be specific chapter with the name phasors, right? They are actually not vectors, but we treat them or we solve them just like as a vector quantities, such as a voltage quantity in primary coil, secondary coil, third coil, and then we put them into head to tail rule, right? But they are not purely vector quantities, right? The reason when we call direction, so direction stands for something very real, just like left, right, up, down, north, east, west, south, round, up, left, down, south, north, even with the degrees, 60 degrees to the north, to the east, right? So the direction should be something physical, real in the 3D space, right? These phasors, they do not have a direction in 3D space. They have a phase difference between them. Just we finished earlier, right? Red, green, and red, blue, right? Those phasor quantities, they have the angle, they have the phase direction, but with respect to each other, those quantities do not have any direction inside the conductor. But the only direction they have, so this is our phasors, right? Then what is vector in electrical engineering? So what are the vectors in electrical engineering? Electrical field, magnetic field. They are real directions, moving left, moving right. So within the conductor, you can feel their direction. You can calculate their direction. Just like in magnetic field, you have a specific direction, real direction. So these are vectors, these are phasors, right? We solve these quantities in power circuits and the electrical circuits. People call sometimes treat them as a vector, but there's a very clear difference between them. Okay, now let's start our real business with the vectors. Okay, uh, from here. Okay, so let's say this is your vector quantity. Okay, so usually we use arrows to represent the vector. We use bold letters to tell the vector this is a vector. Now, how to completely define a vector? Vector is equal to A times A. Now, this is exactly the same I showed you before. Let's say force. So my force is actually equals to, so that means that 5 Newton force along X direction, right? So this small a cap, which is actually X, Y, or Z, tells you the axis. Or you can use, let's say, uh, is it good if I say force on my left hand using, right? If I say or will use X, Y, Z. This is more real, easier to understand, right? Because once you have X, Y, Z axis, it's very, for example, here, this is your X, Y, Z axis, right? This room is a perfect example of X, Y, Z, right? Let's say if I say this direction Y and height is Z, then it's very easy to navigate something. Let's say, for example, if this is 0, 0, 0, and if I ask 2x, then I move 2 centimeter x, right? If I ask 2y, then I move 2 centimeter y. I ask 0z, then I'm standing here. 1z, then I stand 1 up, right? So it's very easy. So these vectors, this A only is a landmark of direction. We call it unit vector. That means its amplitude is 1. So it doesn't make any difference to the intensity. The only difference it makes is to navigate the vector quantity. Just in the case of the previous example, I have force in a particular direction. So we usually write A is equal to XA. This lines also show the amplitude. 6, 9, 2, 11, whatever. And we can simplify because uh, these are some distances. The final product or the final value has some direction. Let's say I am here. This is 2x. This is, let's say, 2 times y. Maybe this is 2 times z, right? So the final vector is from 0, 0 to the final destination, right? So if you move 2 units here, 2 unit here, and 3 unit here, then the final answer is this. Assume there's a small cube and you are at the top, right? So this is the final vector. Now, this vector now can be defined in this way. That means that 2 units on the x-axis, 3 units on the y-axis, 4 units on the z-axis. And then you add them because they are at the 90 degree to each other. So you cannot add 2 plus 4 plus 3, right? Okay, so how to add that? What's the final length of the vector? It's easier to see in 2 dimension. Let's say I am on the ground, right? Here is my desk. I'm teaching here, right? And you ask me that I have to move some distance d or location, maybe location. You send me a location, move here. What's the location? You ask me that take 2 steps along x direction and take 3 steps along y direction. So it's very illogical if I say that, oh, I am at 5. That's not correct, right? So technically 2 point is here, 3 point is here, right? Or like here. Then my final destination is here. So this vector is different from 5. Okay. So how to find out this one? 2 square plus 3 square under root, right? That's exactly what we are doing here. Okay. So we find out the resultant. So in order to find out the magnitude, we take the squares of all the 3 components and take the under root, and then we have a distance from the origin. It's clear. This is what we call amplitude. We call amplitude. Okay. Now we have the amplitude, but how to find out the direction of my new place? Okay, I was here, I was teaching here, and then you asked me to come to a new location here, right? Then what's the direction of my new location? Amplitude, I already told you that I am this meters away from my teaching position. Now, what's the direction? So in order to find out the direction, you take the first vector with the amplitude. So the first vector is this thing. This thing divided by the amplitude, and you will get the final unit vector. So this unit vector will tell you my location direction, where I am. Okay, that's how you can find out the location and amplitude. Now there are certain properties that people use. They obey the commutative property, like if you add 2 vectors a plus b or b plus a, change the order, it's same. Okay. Position and distance vectors. Okay. As I mentioned, if let's say somebody is here at origin and it moves to a location P1 and another guy was also here and it moves to position 2, and this point 1 to point 2 distance can be easily calculated through head to tail rule, right? So you just write on top of one vector and move to another vector, right? It's very, very simple. Now, why we call position vectors. So any point, let's say if you have a point 2, 3, 1, 2 stand for x-axis, 3 stand for y-axis, and 1 stand for z-axis. So what is a position vector? So I can say that, okay, the position vector is this thing. Distance from origin to the point is known as position vector. That's why we use the word O. O is from origin, right? So So the position vector of this position is 2x1 plus 3y2 plus 4z3. Right? This is your position. Or now you have complete values. So I would write this. This is point. People also call it coordinates, right? Usually we work with coordinates, right? 2, 3, 1. In bracket, that stands for x, y, z. So how to write in a vector? So in vector, we write in OP. That means from origin to the point. This vector is now equivalent to 2 times on the x-axis, 3 times on the y-axis, and 1 time on the z-axis. That's how you represent the position vector. Now you see, we will usually use this concept, convert a point to vector. So if you have a coordinates, just use the x, y, and z unit vectors and you can represent into form of a point. Another concept that may be helpful is to find out the point to point distance. For example, in this position, you are here at 1, 1, 1, right? This is your point P1. And you move to 2, 2, and 2. And I ask you what is the distance, right? So you can assume this is your vector, you can assume this is your vector, and you can find out 2 minus 1, 2 minus 1, and 2 minus 1. So how to solve it? 2 minus 1, x, 2 minus 1, y, and 2 minus 1, z, right? So in mathematically, you write this one. Simply subtract final minus initial, that's it. X should be subtracted from x, y should be subtracted from y, z should be subtracted z. So usually we will only consider 3 main concepts. So the first concept is how to represent a vector. Second concept is how to take the amplitude of the vector. Third concept is how to find the unit vector. Right? You should remember these 3 concepts very clearly. And the fourth concept is like how to find the difference between 2 points in terms of a vector. That's it. If there are more concepts, we will discuss them. Okay, now here comes another important product. Have you ever seen this or heard this dot product? Very interesting. That's a dot product. Please. Yes. Cross product is its brother. Dot product and cross product are brothers. So what is dot product? Somehow. But why we have two brothers? Why can't we, combine them? Sorry. Okay, no, I'll make it clear. Okay, listen. There are certain physical quantities that when we multiply them, they are no longer vectors. They are no longer vectors again. I mean, that's a natural thing. It's not that I created it. No, look at this one. Force is a vector quantity, right? I'm applying force here, here, here. It's make difference, right? Force is a vector. Distance is a vector quantity. Moving here, moving here, moving here, right? When you multiply them, what happens? You get work done, right? Work done is joules. Have you ever seen joule in x direction? No. It's a solid quantity, right? So that means if a physical process make use of two vector quantities and the final answer is no longer a vector, we call it a dot product, right? So understand? So it's a natural, right? In electromagnetics, we also see some products, they are vectors and final answer is not a vector. And there's another product where two physical quantities that were naturally vectors, you multiply them and the answer is also a vector. Idea? Any idea? Equal vector. Force and yes, momentum. Torque. Torque is one example. Turning effect. Yeah, if you turn something, force and displacement, and the final quantity is torque. And the good thing about is that if the force is along x and your distance is along 90 degree, remember when you do the torque, right? The force should be 90 degree to the radius. You need to turn it, right? Similar to when you use the key to operate your car wheel or you tighten the car wheel. Yeah, you use the bolt, nut bolt wrench to do that, right? So they're all examples of torque. When you apply torque, force and displacement must be 90 degree. So if you apply like this, the torque should be in the 90 degree, perpendicular to the plane. That's the perfect example of the scale, the vector product. Therefore, in order to model them properly, we have very beautiful formulas. So this is our one vector quantity, another vector quantity. This is the angle between them. And when we have a third quantity, we call AB cos theta, right? So the final answer is no longer a vector. I give you the example of a work done. Okay. Now, this one is also commutative, distributive. It holds these properties. You change the order. Now, uh, A is A amplitude, and if you know the dot product, you take the dot product and take the under root. It's also equal to the amplitude. That's a very beautiful thing because A dot A is A cos theta, and the angle is 0. So cos 0 is 1. So A dot A is A square, right? So this is another trick to find out the amplitude by using the dot product. Another thing, if you find out the angle between them, you know they're the vectors. So you use AB, this is the A magnitude, this is B magnitude, right? And take the angle, take the cos inverse, you can use this is just from this angle. Now, this is important in our subject. Okay, because when we solve some electric and magnetic field problems, we will see that if two quantities are on the same axis, they are actually at perfect position, right? Just an example of the force and displacement, right? Because force and displacement both are on the same line, right? If they are on the same line, the magnitude one. If force is along the x direction, distance is along the x direction, x dot x is 1. Why is 1? Because x dot x is xx cos theta. Theta is cos 0 is 1. Okay, let's write it so you can remember. So let's say this is your force and this is your displacement. Okay, force is along x direction, displacement is along x direction. So F dot D is equal to F dot D cos theta. Okay, now F is replace vector with its form. So where is the form? magnitude direction. Okay, so F is now equal to F and X. D is equal to D and X, and then cos of theta. So FD is FD, these are the constant. X dot X is 1, right? Because why it's 1? Because this is X and this is X. X dot X is equal to X cos theta. Because a unit vector, magnitude is 1 and angle cos 0. Cos 0 is also 1. That's why it's 1. Because they have theta equals to 0 degree. That's why it's 1. Cos 0 equals to 1. They are 0 because the angle is 90 degree and cos of 90 degree is 0. That's the reason when you lift the box up, technically the work done is 0 because force and displacement have 90 degree. Right? If it is 90 degree, then cos 90 is 0. Right? So in physics, we call it potential energy. So you convert that energy into potential energy. Right? Like when we lift it, it again goes back. But there is no work done. Work done is when we move it along the direction. So that's why if you take if you want to have a good advantage of the scalar product, make sure that the both vectors are along the same direction. As long as the angle between them increases, the work done decreases until they reach 90, the work done is 0. Therefore, you see x and x have a 0 angle, y and y have 0 angle, z and z have a 0 angle. That's why their value is 1. Therefore, we put 1 and then 1. Therefore, 1 here. FD is maximum. Okay? But when x and y, if one quantity is along x, another is along y, angle is 90, cos 90 is 0. Okay? That's the only concept we will use. But again, when this concept again arrives in our subject, I will repeat it. This is another critical concept. So this is the cross product. Some mathematical or physical principles are best explained through cross product. We will see later on. For example, magnetic field and the force generated into the coil. You will see that two quantities they result in third quantity which is actually 90 degree to each other. Right? So another people use the term right hand rule to describe that if two vectors are along the axis of your curve and the third hump actually determines the direction of quantity. In another people use like this. One quantity, another quantity, A, B, and this is final. Okay, so therefore we use this N. N stands for normal. Normal means that this 90 degrees to the plane, perpendicular to the plane. This is called normal vector. Okay. So if one quantity and another quantity are at certain angle, their cross product is due to the sine theta between them, and the final direction is here. And also a vector quantity. Product is also a vector quantity. For example, if A could be a magnetic field, vector quantity, B could be another displacement, vector quantity, and this final term could be, of course, another vector quantity. Okay. So A cross B is not equal to B cross A because the order of the forces or order of the vectors is important. If AB is up, BA should be down. The minus sign shows that the force or the resultant quantity will be downward. This is also very important when we will see how the magnetic field helps our conductor to rotate inside the coil and produce the force. So one coil moves up, another coil moves down, and that's how the motor starts rotating. Understand? You will see it. So that's the negative side. So negative A cross B is the order of the multiplication. B cross A is the reverse order. So they are same but opposite in direction. Okay, this is important. X cross Y is Z. Why is that? So remember X, Y, and Z, they all are 90 degrees to each other. You all know that. So X, these are X, Y, Z. These are 90, these are 90. X is 0, Y is 0, Z is 0. But X, Y is 90, Y X is 90, Y Z is 90, Z X is 90. That's how the components, rectangle component in 3D looks like. Now, X cross Y should be equal to Z. Because in cross product, the final answer is perpendicular to the plane. Right? If one quantity is X, another quantity is Y, the answer should be in the Z. Understand? Just like this. X, Y, and this should be Z. Because it's 90 degrees to both of them. If these are X, Y, Z, it should be X. That's the only possible 90 degree. And another thing, there is a cyclic order. Okay? Remember, this is cyclic order. What does it mean? That means that X, Y is Z, but Y axis minus Z. Okay? ZY is minus X, XZ is minus 1. So XYZ, XYZ, XYZ in the order. XYZ, XYZ, XYZ. So this is cyclic. Okay. Similarly, cross product with each other is 0. X cross X. That means that the two quantities, they are along the same direction in cross product. Their effect is 0. That's how we will see that when the magnetic field and the length of the conductor, they are like same direction, there is no force. There is no force. Therefore, you see that in the motor, the coil are along the 90 degree to the flux. The flux passes A. The two terminals of the coil, they produce force. But these terminals, they do not have any effect because they cancel. Because the length and the flux, they are same direction. X cross X is 0. We don't have any turning effect on the top and the back position below. That's why we need to look at the vector. Because field has the direction, length has the direction, like we have the direction, distance has the direction. That's how we play. Okay, that's how we use determinant to find out the vector quantity. Okay. Okay, these type of questions, these are not for the exam, okay? But there's a purpose why we include, okay? The reason is so you should have a practice. You should learn, I mean, how to play with vectors, okay? This is for your own understanding. Similarly, we have triple products. And finally, we have a Cartesian coordinate system, okay? Let's spend 10 minutes on it to understand the system, and then we can finish the lecture. Okay. As I mentioned before, anyone who has seen this system before, because on the vectors we have already discussed this. So the Cartesian coordinate system is similar to a cube, right? Just like your classroom. So we have X direction, we have Y direction, we have Z direction. Okay. Now, in order to solve this, because remember, when we are solving some quantities, uh, for the sake of finding the area, for the sake of finding the length, for sake of finding the volume, we need to take help of differential calculus to find out the the parameters. For example, for for finding the flux, we need to multiply the magnetic field with the area. In physics, we learn flux is equal to B times area, right? It's very simple. B times A. Area is simple. If the length into width, right? It's very simple. Length into width is the area. Okay, but if the conductor is cylinder, then you need to find out the area of a cylinder, right? It's also very simple. But that's true only when the cylinder is full. What happens if there is small part of the cylinder responsible for the area and we have to remove the other part? That's how we use the differential calculus. So we have to design a formula that for every possible shape, square, I mean the cube, sphere, or cylinder, if we know the dimensions of the three quantities, we can calculate the area, length, and volume by ourselves. And when we solve the quantity, we only use the limits, and then we can solve. Now, uh, we will discuss three things in three systems. First one is Cartesian system, and within the system, we discuss three things. Look at these three small chunks of a cube. These are called the differential calculus. We will actually find differential element, and then a particular length or width or volume, we use the limit of integration to solve it. I will later show you. It's very simple. We can consider there are three differential lengths: dx, dy, and dz. It's very simple, right? There are three lengths. We call them dx, dy, and dz. Okay. So how to find a complete length? Later on, we will do like this: dx from 1 to 2. If the unit is x, solve it. Then you can find a complete length. Later on, we will do it. But currently, just consider this. How about the area? So in this cube, we can have three different areas: top, side, front. Every cube has three possible areas, right? Surface areas. Okay, so what are the three? So top and bottom are actually same, right? So you consider top. Front and back are same. Consider front. Left, right are same. So there are three possible combinations. This area, you see this direction is along this. So for every area, we say that direction of this area or the face of this area is like this. Right? What's the direction of my face towards you? If this is x, this is y, then if I ask you to calculate the area, x times y, and direction is z. Understand? So exactly the same thing. For example, the area we call S, that means surface. Surface along x direction is due to y and z. If you take the z part, x part, multiply them, you will get x direction area. So now consider any rectangular shape, right? For example, this is rectangular shape. This is 2 centimeters, this is 4 centimeters. Okay, 2 times 4 is 8. If this is x, this is y, this is z. I ask you, this surface is along z direction. 2 times 4, z is this area. What's this area? X, z. Right? What is this area? X, y, z. So there are three possible areas. right? So all these three possible areas are this, and this. So for X, we use YZ. For Y, we use XZ. For Z, we use XY. Is this clear? These are the three possible areas. Okay. Now, what's the volume? X times Y times Z. 2 times 2 times 3. So this is the 3 point. So these quantities, all those formulas are summarized in this table. But we will go through each, the coordinate system. But actually, you have to understand it. I'll give you this in the example. Okay, for example, this is our coordinate system. So what is the length? Look at the length. We discussed this. Okay, the dot product is given. Everything is given. Okay, look. The only thing that you need to understand is these three columns. That's it. These two we will study later. Look, length dx, dy, and dz are three lengths. There are three surfaces. Remember, three surfaces: top, this one front, and side. One is along x direction. Let's say this is xy, this is z direction. So if it is x direction, we use x. If it is y direction, we use y. If it is z direction, we use z. Understand? So how to find those x direction? Multiply with the y is x, z is y. So how to find the volume? Multiply three of them. Yes. So that's called the rectangular coordinate system. Okay. We will study two more coordinate systems in our next chapter, next lecture, and we will complete this table, and then we will solve the problem. Okay. Now, please take some time to look back at your topics and you can have. Please spend some time on your notes and mark this that you want to speaking of, if you are very close to it, you will get very down. How much air in the very small now? And somebody has air. Exactly. That is not funny. The medium knowledge is how we are. Maybe distant because of what the question is that if it is then how much distance so output value is this. Input value is this. That is the distance. That is almost okay. So let us continue on. And I want to it's not going to be but this nothing can be changed. Remember, I said in what is record and what is how it's all we are working towards It's very easy. Some places. But you should try to make up so the alpha more larger, and then you see that it's good. For example, look at this. Look at this. Now alpha is 0.5 here, right? So in order to find the z is equal to -2/3/4. If alpha becomes bigger, this 4% becomes smaller. So yeah. So it means that alpha is small can have the. So actually, alpha is this is the attenuation rate. So every alpha has a attenuation. Alpha means alpha 1. If medium is so small, maybe it's like this. This is like if the medium is really bad, alpha is. So that's the alpha that controls the decay. This is the same decay factor that you see in the capacitor. Capacitor charging and discharging. That's the time constant in the capacitor. Oh, that is T over walk. Right? That can be controlled by the capacitance and the resistance value. So if you have a higher time constant, then the capacitor will take longer time to discharge. Same function you will see T is from minus T over tau. You need the same function in capacitor. So same curves for the capacitor. Yes, exactly. So rate of decay is this is the exponential decay. In capacitor, we also use the same concept, but there we don't have alpha. We have minus T over tau. Tau is the RC time constant. Right?